and welcome to tonight's TI Technology webinar hosted by Texas Instruments Australia. We are really excited to bring you IB Mathematics Studies with two very experienced IB teachers, Bojana Graham and Joanna Cipriano. My name is John Beaumont, and I'm your host for this event. I teach mathematics to Years 7 to 12 students at O'Loughlin Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. I'm excited to introduce our first panelist this evening, Ms. Bojana Graham. Good evening, Bojana.
Good evening, everyone.
It's lovely to have you with us. It was fantastic last week to have a standard level IB workshops. If you missed that one, please look at it on demand. And now another one for studies. Certainly keeping you busy tonight, Bojana, so thank you. As you can see, Bojana is a very talented mathematician. I know she's a fantastic senior mathematics teacher at Wesley College in Melbourne, and she likes to continually challenge herself and share her knowledge with others through key roles with VCAA, IB, MAV, Pearson's Australia, and Pomoja Education. So, Bojana, thank you very much for joining us this evening and sharing with us some of the technology aspects of the TI calculator that you use in your classroom.
Pleasure.
Our second panelist this evening is Ms. Joanna Cipriano. Good evening, Joanna.
Hi, John. Hi, everyone.
You know, I know how to pronounce your name, but every time I see it, I freeze and I think, oh, no, I'm going to get it wrong again. So I do apologize. Would you like to tell everyone how I pronounce your name properly?
Well, the way you did it was perfect. Just Cipriano, 100%. You did it.
Cipriano. Thank you, Joanna.
You're just doubting
yourself. Joanna taught all levels of the New South Wales HSC and IB. Joanna's experience with TI technology, supporting peers and students, epitomizes what our webinars are about, which is teachers teaching teachers. And she has taken this a step further by producing 2 iBooks, which are available online. And Joanna's dedication was demonstrated with her winning the Outstanding Supervising Teacher Award from University of New South Wales in 2017. So congratulations for that, Joanna.
Thank you. It was quite a surprise.
Oh, wow. I think it's fantastic. Well done, you. And it must have been, so when you say supervising teacher, that's people, you're working with student teachers who are going to become math teachers?
Exactly, yes. And so I had her in term 4, and she's almost graduated, and yes, she nominated me, and that was a bit of a surprise, I have to say. So yeah, it was lovely.
Well done, you. Well done.
You.
That's the intros done, and I'm going to pass you over to somebody who's much more important and who you've tuned in to listen to tonight, and that's Bojana Graham, who's going to start us off on the first part of the webinar tonight, which is topic 6 from the studies course. All yours, Bojana. Thank you.
Thank you. Good evening, everyone. So I will start with looking at mathematical models, and Joanna will look at introducing differential calculus. So these are the topics from the guide for IB studies. We look at linear models, quadratic, exponential, other functions of this form when m and n can be positive or negative integers. It's very important for the students to draw accurate graphs, concept of a function, domain, and range, and good habits when labeling the graphs with some indication of scale. As we know, studies is a very different group of students, and they're not good algebraically, so they need to get the help from their calculator as much as possible, and they can have a calculator for both papers. So we'll start with linear models, and typical questions will involve issues with revenue versus cost modeling, profit and break-even models. And those could be linear or linear and quadratic combination. So I've chosen the first question here, like a typical question when we produce some books, and there is a fixed cost of printing process, and then there is a cost per book as listed here. Then the books will be selling at $9.50 each, and we don't restrict the market here. So the students are to determine the cost and revenue functions, graph those functions, answer how many books must be sold in order to break even, and then say what level of production and cost will generate 10,000 profit. So I will start on a new document and I will add a calculator. I always teach my students to use as much as possible a define function, which is menu 1 actions defined. So let's define those two functions. Our cost C in X is equal to the constant component, which was 6,000, plus we had, it was given 3 to 50 over 1,000 books. So if we divide by 1,000, it is the cost per book, and multiply times X. So that's how we define the cost function, and then we do the same thing and define the revenue function. Students should know that the calculator does not distinguish between capital and small letters, so they can't use capital ones and small other ones. It will not make any difference. So after a class discussion, they would say that the break-even point is when those two are equal. So in this situation, we would use numerical solve, and we try to solve C in X equals R in X, and we solving for X, and we get that it is 960. Of course, it is nice to see also how it looks graphically. So if we add graph, and we already defined those functions, so we can say C in X, we might restrict the domain here as a good habit, because of course it only really makes sense when X is greater equal to 0. Won't see anything because we need to adjust the graph, but let's open it again and put the revenue function here, and similarly we would restrict the domain because it only makes sense in this context when X is greater equal to 0. And again, we see a bit of the function here. So students can either zoom out somewhere there, which doesn't work that well, or of course we can try to play a bit with the enter, let's say go -10 here. We know already that it was 960, so we need to go a bit higher than those values. And similarly, we need to change the window here to higher values there. So that's really important skills for the students to learn how to do those things, to be able to see the graph. So now we can see the cost function and the revenue function. So clearly, if the revenue becomes bigger than the cost, that's when we start getting some profit, and we can obtain the same things by finding the point of intersection. The other way we can also do it, so I have those done here, we can sketch the profit function, which is revenue minus cost, and when profit was negative and then 0 starts being positive, that's when the break-even point occurs. So these are some good habits for students to learn, doing those things this way. And we can also check solving the profit function, as I did here. Define profit is revenue minus cost, and solving for 10,000 because that's what the question was asking. So we need to solve that many books, then the revenue is 24,320. That's the cost, and the difference is 10,000. So these are the typical linear models questions. When we get to quadratics, there are two types. One is questions in context. Some other questions are just quadratic functions. Again, students are not supposed to be able to factorize or do much algebraic manipulation. They just need to be able to use the calculator and think. So we have one x-intercept and the turning point given. That's the general rule. We need to find the other intercept and the constants A, B, and C, the coefficients. So in class, we would start by saying, okay, if that's 0.4 here, and that's a turning point or a vertex, so we know that the vertex is halfway between the x-intercepts, and the axis of symmetry passes through the x-coordinate of the turning point. So in class discussion, we would have got those values, 4, 0, 1.5, minus 2, and 0. Now, we still need to find the coefficients, but given 3 points, of course, what we can do, we can get the spreadsheet, and if we call this x and we call this y, we enter our points. So we had 4 and 0, and we had minus 2 and 0, the two x-intercepts, and we had the point 1 and 5. So now we can perform the quadratic regression to get the coefficients A, B, and C. So we can do it in the spreadsheet. Start calculations. Oops, I pressed too fast. Statistics, start calculations. Oh dear. Menu, statistics, start calculations, and quadratic regression. So we have x and y. It will save the equation as well if we wish to. But, well, if we look at those coefficients, they are decimals, so that's not ideal. But it's not a problem, because if we go to the calculator screen, we can retrieve those coefficients. So let's say if I take, if I go to variables, I've got statistics A, and if I enter here, it gives me a decimal. But if I go to number, approximate to fraction, it will change to a fraction. Similarly, if I get B, I get a decimal here, but I can change this to fraction. And that's very useful for study students, because they often ask actually for some values like that, and later even in linear changing to ax plus by plus c, where a, b, and c are integers. So that will help them greatly with those calculations. And again, changing to approximating to fraction is very helpful. So once we have that done, if I go back to here, knowing the coefficients, we can enter the equation and check that actually this parabola passes through those points. So that's the check for the students that they've got this answer correctly. Some other typical problems are when we have a situation in context, like here we have a garden area which is a square of side x plus 1 meters, and then we cut the corner of the square, which is again a square of length 1 meter. So what the question says here, that the whole area but the square is for roses and this corner is for grass. So we want to find the shaded area. I didn't quite shade it, but that's the area but the square. So write down the expression. Then we want to find the value of x given that area is equal to this. And then we want to put a fence around the roses area and find the length of this fence in this particular case. So again, if we look at the question, which I actually have in a separate thing, so clearly the area, the shaded area will be x plus 1 times x plus 1 minus 1. So if I start a new document, I can again define this function and can call it a, I might actually put a new problem because I did it in this document, so that will work better without being a problem. So go again, actions, define, and I say A in X equals. So we had X minus 1 squared and minus 1. So here they don't need to expand, they don't really need to do any algebra, because if they say define, it will work. Now we were given the value for area, so now if we try to use numerical solve for this given value, of course we could have a good discussion with students. What happens, it is a quadratic, so if we just try to solve for X, we get a value which is not valid for a dimension, but knowing it's a quadratic, it only has 2 solutions, so we can easily overcome that by saying that our X is actually positive, so then we'll get the answer 11.5. I can store this value, which is also a good idea for the students to learn how to do. I can store this value as D, let's say, and then we were asked to find the dimensions of the fence, so we would have 2 times D plus 1, and then we would have plus 2D. So it will be using the value which we already predefined. So that's again something students should learn how to do, especially when the values are not exact values and they wouldn't be using rounded values, but if they store, they can use the whole values. Exponential models, population growth, radioactive decay, cooling of a liquid, spread of a virus, depreciation. These are the very popular topics. So I start with a very easy example. The number of people is given by this formula. Calculate the number of people present at the start after 4 years and how long will it take for the population to double. So just have a look what I did, because that's similar to what we already talked about it. So we defined n in t, and once it's defined, we can find n in 0, n in 4. And again, it was asking to the nearest integer, and we can solve and get the answer when the population doubles. So originally it was 120, so 240 is when it doubles and solves. Once we have the function defined, we can also sketch it. And when we have the graph, we can also find when the population doubles graphically. So the define feature on the calculator is very powerful and works very well, and I always encourage my students to use it as much as possible. This other question on exponential growth is a bit more complicated because the equation is actually more complicated. So we have a concentration of drug in the patient's body here after T hours, and it's given by this formula. We want to find the concentration after 3 hours. It also says initially the concentration increases until it reaches a maximum and then decreases. So again, find the time when the maximum occurs, what's the maximum concentration, and so on. This time I decided I will start with the graph. It draws nicely in the standard window, as we can see, and I actually restricted the domain greater equal to 0 here. So we see that the initial concentration increases, reaches maximum, and then less. If we actually change the value, then the graph would look different. So it's also a good practice for the students to know that in different windows the graph will look differently, and they need to pay attention if they ask them to copy the graph to the given set of axes. They need to set up their window appropriately, because otherwise their graph, of course, will have a slightly different shape. Now, the other question asks after what time the population is 1.9. So that's really a good discussion in class that solving this question graphically is the preferred method, because if we solve using numerical solve, we'll only get one answer, and that's not what we want. So clearly, if we sketch a graph here, we get two answers, and that's what the students should be practicing. Other functions look at vertical, horizontal asymptotes. Define and table of values are very useful, particularly with asymptotes if students have difficulty with those. So I've chosen this function 2 to the power of x over x minus 1, and we want to find the y-intercept, the minimum value of x for x greater than 1, write down the equation of the vertical asymptote, find f in 5, and sketch the graph. So again, if we define this function, we can easily find f in 0, which is the y-intercept. And we can find the values at other points as well. Now, if we sketch the graph, we can clearly determine the minimum value when x is greater than 1. The students will not quite see the asymptote, but if we press Control-T, and the students will scroll through the values, so we see that the function has some numbers until we get to x equal 1, and it says undefined. So that's an indication for the students that we have the vertical asymptote when x equals 1. Now, they will not be asked about this horizontal asymptote, but in some other cases, if they, of course, scroll to smaller and smaller values, so that allows to find the horizontal asymptote, because we can clearly see it's getting closer and closer to 0. But the vertical asymptote is quite nicely done from the table. Whenever we have the undefined value, the vertical asymptote occurs. So that's not too hard for the students to see and understand. Now, another question is a modeling question. We have a card box is to have a fixed volume of 36 centimeters squared, and the width of this card box varies according to this particular function, x plus 6 over x. And they say this is the graph of Wx between 0 and 7. So that graph would be drawn in the exam. And then they say use the graph to complete the table for the width function. I didn't put the values, but of course, whatever it is. So we need to have only positive values, and scrolling down and up will allow the students to complete the value. So the table is very useful in various contexts. Now, the length is defined by the function L in x equals x. So they say draw the graph on the same set of axes. So if we draw this graph here, we see that they intersect. So that's width, that's length. And the other question was asking, determine the value of x which produces a square base. So after some discussion, they would arrive that width has to be equal to the length. So finding the point of intersection gives us the answer. And also, if we go to the table and look up at those two values, so if I make it a bit bigger, we see that the width and length is equal values. They're equal to 3, but it's just a coincidence here. So that's how those things can be done. Now, this question is about comparing models, and it's probably also some good introduction to their internal assessment if some stronger students want to do some modeling, not necessarily a statistics project. So we have a table, and it says this is a population of bacteria is growing as shown. So we want to plot the graph of N versus T, answer those two questions. So they are just from the table, initial 320 doubles. And then we are to fit 3 models, a linear model, a quadratic model, and exponential model, and answer which is the best. So this is just comparing the models. So I've pre-entered the values for T and N. And this time I will be using the scatter plot because that will allow me to actually enter the other functions as well. So if we go to graph entry and look at the scatter plot, so I had already T here and I had N, and of course I will need to change the scale again because otherwise it will not show. I might be here, and we were going to about 1200, so we get a nice scatter plot. The advantage of a scatter plot here is that I can now enter my other models. So if I open the entry line, I can change it back to a function, and my linear model was 300 plus 55x I need to use in this. So you see that the linear models, it's reasonably well for the first 5 points, but then of course it goes off on the tangent. So then if I enter the quadratic model, 300 plus 5.5x squared, this is generally really not a good fit at all. And our third option here was an exponential model. They all, of course, start at 300 times 1.15 to the power of x. And clearly this exponential model fitted very nicely. I could do the exponential model in statistics graph if I just put T here and N and do the analyze regression and put exponential. So as you see, it's pretty similar to 300 times 1.15. But in this view, I cannot actually enter other functions as I could see here. The last one is looking at the question where we have, again, exponential model. So this is about the ants colony, and I did here the MS notes document just to save some time. So again, if I define the function, I can find the initial number very easily. I can find the number of ants after 2 months. Then solving this equation, again, will tell me how long it will take to reach 25. And then the last question here is determine the equation of the horizontal asymptote. Again, many students will struggle a bit seeing it from here, but if we sketch the graph, they could do two things. They could guess it's 30, or again, they could use the table, and if we scroll down, clearly we see that this number will not go over 30. So that's what I had to present today. Thank you for your attention. And now Joanna will talk about Introduction to Differential Calculus.
Fantastic. Fantastic, Joanna. Thank you very much indeed. There was a lot there to take in, and I was reflecting, thinking how lucky your students are to have somebody who's knowledgeable as you teaching them. You just flew around that screen fantastically, and it's great that we've got it on demand so people can rewatch again. Sorry?
I do it much slower in class.
Well, I think that's the advantage of having it on demand, is that really everyone got the flavour of it, and there's some nice feedback from people saying some of the things that they picked up already. So thanks for sharing that. And as I've said, those documents will also be available as part of the on-demand package afterwards. So thank you very much for your time, and thanks for sharing that with us. That was excellent.
Thank you.
Joanna, I can see your screen. All over to you.
Wonderful. Thank you, John. Hi, everyone. I'm going to be going through topic 7, which is Introduction to Differential Calculus. That's in Studies. Okay, so we'll do a few examples, and then of the basic skills, and then we'll do a few exam-style questions. Okay, so example 1 is, to consider the function fx equals x cubed minus 4x squared plus 1, we want to find the gradient of the tangent to the curve at the point 2, -7 using, we're going to do the derivative function in the calculator document, and we're going to use the graph. Okay, so first things first, I'm going to open a calculator document. So press on, calculator. Okay, and I want to use the derivative function, so menu, calculus, and I want numerical derivative at a point. Okay, so my variable is x, and my value, that's my x value, and it's 2. And of course, I want to use the first derivative for the gradient, press OK, and here we go. So let's put the function in there, so it's x cubed minus 4x squared. X cubed, get out of the power, minus 4x squared plus 1. Okay, press enter, and we get -4, so the gradient is -4 to the tangent at x equals 2. Okay, so now let's try the graph, see if we get the same answer. So click on graph. Okay, so let's just graph x cubed minus 4x squared, x cubed minus 4x squared plus 1. Enter. Okay, so I want the numerical, the gradient. So let's go menu, analyze graph, and I want dy dx, and I want it at 2. So it's a little hard to trace the graph exactly onto 2. So what I'm going to do before I press anything else, I'm going to press 2 on my calculator, and then there it is there, it's showing up. Take it in the input, press enter. And now let's find the numerical gradient at the point where x equals 2. And we got -4 again, so we know we're right. Sounds good. Okay, next question. Find the equation of this tangent. Okay, so let's go back to the graph. And I'm on menu. Now I want to go down to geometry, points and lines, and choose tangents. Now having the point already there is actually really helpful. So if I go over there and click on that point, immediately the tangent shows up. So it's y equals -4x plus 1. Now, before I go any further, I just want to show you what else you can do with the tangent. So if I say menu, geometry, points and lines, tangents, and I'm not sure where I want it, I just click the curve of this graph, and I'm just going to put it in a random place there. Okay, so there's the tangent at that point. But what's kind of cool is I can grab this point and drag it around the curve, and the tangent changes. So I go up, 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 and look at this right here is the maximum, horizontal, and then go down again, horizontal, up. It's pretty cool. But what's nice about this is it's really explaining the whole idea of positive, negative, and zero gradients, where they are, what it looks like. So here's a positive gradient. So it's a really nice tool to use in the classroom when explaining the positive and negative gradients of your of the idea of tangents to your students. Sorry. Okay, let's keep going. So I'm just going to delete that now.
Joanna, do you need to, I know that you were saying that your throat was a bit sore tonight and not great as a teacher.
Yeah,
no, don't have to apologise at all. You go have a quick drink. There's no rush.
Yep, thank you very much. No, I'm feeling much better now. Thank you, though. Okay, so now we're going to find the next question, which is find the coordinates of the point where the tangent crosses the curve again. Now, at the moment, I can't see it. My tangent's too small. I can't see it. I know it's going to cross somewhere up here, but I can't see where it is. So I'm actually going to graph the line, -4x plus 1. So press tab and type in -4x plus 1. Enter. Okay, so now I can see the proper tangent much longer, and I can see it intersects here. So now I can find the point of intersection. Menu, analyze graph, intersection is the lower bound, upper bound, and there we have it. So the other intersection where the tangent crosses the graph is at 0, 1. Okay, so now the next question is find the equation of normal at the point 2, -7. Now, the method I'm going to use is unfortunately not available in press to test mode. So, but it might be good to show in the class so students can follow and check their answers. Okay, so I'm just going to move this over so we can see things a bit clearer. Okay, we're going to go menu, geometry again, points and lines, but this time, sorry, I apologize, is construction, and choose perpendicular. Okay, so I want it to be on the same point as before, so I'll click on that point, and I'm going to choose this line to be perpendicular to, and there is my normal. Now, but I want to know more about it. I want to know what the equation is. So I've clicked on my normal, press menu, actions, coordinates, and equations. And of this line, click on the line. Oh, it's breaking out. Okay, here it is there. So the equation, so my equation of my normal is negative 2.25 x minus 7.5. So there it is there. Okay, find the coordinates of the point where the normal crosses the curve again. Okay, even though I can see where it's crossing, for whatever reason, it doesn't seem to like me trying to find the intersection, so I'm going to graph that line again. So press tab, 0.25x minus 7.5, and there's a nice long line. And now I can find my intersection a lot more clearly. Okay, so menu, analyze graph, intersection. Now I've got a million graphs there, so it's asking me which graph are you talking about. So I'll click on the purple one and the red one and choose my lower and upper bound. Okay, so I've got a lot going on. Here's the first point of intersection, and we'll just do it again. Again, at this graph and that graph. Here's my lower bound and my upper bound, and there's the other point of intersection. Okay, so we've answered all the questions there. Okay, so now we've got example 2. Consider the curve fx equals x to the 4 minus 3x squared plus 7x minus 1. Find the coordinate of the minimum point. Now we've got a couple methods we're going to try. The x coordinate, I should say, using the graph or using the NF-min function in the calculator document. So let's try the graph first. So I want to open a graphs page, and I'm going to graph that function there. So it's x to the 4, get out of the power, minus 3x squared plus 7x minus 1. Okay, so there's my curve, and I want to find the x-coordinate of the minimum points. So menu, analyze graph, minimum. It's actually okay that I can't see the minimum right now. So let's go to the left of where we believe the minimum should be, and then the right, and here it is there. Okay, so it is at negative 1.61 and negative 13.3. So, but the x-coordinate obviously is negative 1.61. Okay, so let's now have a go at opening a calculator document and asking to use the menu calculus, the numerical function minimum. So I want the minimum of the curve x to the power of 4 minus 3x squared, plus 7x minus 1 again, apologize, Okay, let's go back in and comma x. I want the x coordinate, and there it is there. So negative 1.6. Now they've given us more decimal places, but it would be negative 1.61 just like on the graph if we rounded through significant figures. Okay, and as you saw, when we went to calculus, there's also a similar function for maximum. So menu, calculus, we've got the numerical function if you wanted to find the maximum. Okay. Now I want the minimum value. So the reason I'm asking that again, it seems like I'm asking it again, but it's important for students to understand. When we're asking for a minimum point, we want both coordinates, the x coordinate and the y coordinate, but the minimum value is just negative 13.3, the y coordinate. So it's just important that students understand the difference. Okay, now the domain in which y equals fx is increasing. So the best use for the function here, so we can see that the function is increasing after the minimum point. So it's when x is greater or equal to negative 1.61. So that's the domain. Okay, so now let's find the x values of the stationary points using polyroots. Okay, so we've already got the x value because it's only got one it's only got one stationary point, the minimum, but this is another way to find the x values of the stationary points. So essentially, we're putting in the polynomial, the function, and making it equal 0. Sorry, we're putting in the derivative because stationary points are when the derivative equals 0. So for this curve, the derivative would be 4x cubed minus 6x plus 7. So we want to know when that derivative equals 0 because that'll give us a stationary point. So if we go menu, algebra, polynomial tools, find the roots of a polynomial, okay, the degree of our derivative would be 3. So press 3. And it's 4x cubed, so we put a 4 there. There was no x squared function, so x squared term, I should say. And then minus 6, so negative 6. And the constant was just 7. Okay, so I want to solve the derivative equals 0. And as you know, for polyroots, we don't need to put equals 0. And again, I get the same x value as with the previous methods. So there's a few different methods of how to find the x coordinate of stationary points. Okay, so now we have some questions based on exam questions. So a function is given by fx equals 4x cubed plus 3 over x squared minus 3. Write down the derivative of f. Okay, so let's write it down so we don't forget it. Menu, insert, math box. Okay, so the derivative would be 12x squared. Now, here's the thing. We have to remind our study students, make sure they write this in index form, so it would be 3 times x to the negative 2 before they differentiate it. And then it will become negative 6x to the negative 3. Because minus 2 minus 1, negative 3. Okay, and then the 3 is a constant, so it's nothing there. So that's the derivative. Now, find the point on the graph of f which the gradient of the tangent is equal to 6. So in other words, I want to know when this derivative function equals 6. So I can use nsolve for that. I wouldn't use polyroots because it's not a polynomial because the negative indices. So I'll go on, calculate, okay, menu, algebra, nsolve of 12x squared minus 6x to the negative 3, and I want that to equal 6. So cross equals 6, and I want to solve that for x. Enter. Okay, so the point where the tangent, gradient of the tangent is equal to 6 is where x is 1. And we've asked for the point, so I have x, but I don't have the y value, so we just put 1 in there. 4 plus 3 minus 3 is just 4. So the point is 1, 4. Okay. Now I want to find the minimum value of f on the domain between -1 and 5. Okay. So I better graph the function. So let's open a graph page. And it's 4x cubed plus, okay, 4x cubed plus 3 over x squared. Get a fraction, 3 over x squared minus 3. Okay, so here's the graph, and I want to know the minimum between -1 and 5, so on the domain. Now, we can go menu, analyze graph, minimum. Now my lower bound, before I do anything, I'm just going to type in -1 and press enter. Okay, and now add the upper bound. So it actually asks for lower bound, but if I move my cursor over here, it'll ask for upper bound. And now I want to type in 5. Okay, now look at that. It's given me the minimum stationary point. But we can see from -1, which would be when x equals -1. So if I graph that, oh, sorry. So if we think of x as -1 here, and x is 5, it's about there, we can see that this down here would be much lower than that. So we actually haven't got the minimum value by doing that. We've only got the stationary point. So as we know, study students should be checking the stationary point as well as the points on the end of the domain. So if we go menu, geometry, points and lines, point on, and immediately I click on that graph, and I want it on -1. Sorry, that's right. I actually graph the point on the graph, and then I change the x coordinate. Okay, so I have to play with that a little bit. I'm going to change that to -1 and press enter. And now look at that. My minimum value is actually -4, not 3.6. And we can also check 5. You could get into the habit of getting your students to check both endpoints of the domain. So geometry, points and lines, point on. Again, I'll click on the graph. Okay. But I want to change this to 5. Okay, well that's well above where we need to be. So if I change that to maybe 40 or something, okay, it's still got to see. So obviously for 5, we're way too high and it's not going to be a minimum. So obviously my minimum value between -1 and 5 is actually -4. So it's a good habit for students to check the minimum stationary point and both ends of the domain. Okay, exam question 2. This is like an optimization problem. So a shipping container is the shape of a rectangular prism with the dimensions. The width is x, the length is 2x, and the height is 12 minus 3x. All the measurements are in meters, and the volume of the container is given by that expression there. Find CVGX. So let's just write that down. Menu, insert, math box. Oops. I'll try again. Menu, insert, math books? Okay, so that would be 48x minus 18x squared, the derivative of v. Okay? Find the value of x for which v is a maximum. Okay, so let's graph the function. On graphs, okay, and we want to graph 24x squared minus 6x cubed okay, and I want to know when it's a maximum. Okay, so let's have a look. Now, obviously, x has to be positive because it's a length. So let's go analyze graphs. Maximum, somewhere from here to here, and there it is there. Okay, so the question was find the value of x for which v is a maximum. So x is 2.67. But the maximum volume is the 56.9, so it's important that students actually understand what these numbers mean. It's easy for them to get mixed up and get the interpretation of the numbers mixed up. So it's important that they realize the function inside is the first one, which is the length in this case, and this is what it equals, which is the v. So this one here was 2.67. And the next one, which is find the maximum value, was 56.9. Okay. And then find the length and height of the container for which the volume is maximum. Okay, so that length was 2x, and the height was 12 minus 3x. So the length would equal 2 times 2.67, so you can just do it on a calculator document. So on calculator, 2 times 2.67, 5.34, and then the height is 12 minus 3 times 2.67. So 12 minus 3 times 2.67, which is 3.99. Okay. We'll leave the next bit for now. And then exam question 3. Consider the function fx equals negative x to the 4 plus 8x squared plus 5. It is known that at the point where x equals 2, the tangent to the graph is horizontal. So find f dash x, so that's obviously negative 4x cubed plus 16x. And then write down the coordinates of these 2 points where there are the 2 other points in the graph at which the tangent is horizontal. In other words, I want to know when the derivative equals 0. So I can use polyroots for that because it's a polynomial. So I'll open a calculated document, menu, algebra, polynomial tools, find the roots of the polynomial. Once again, the degree of the derivative was 3. So it'll be negative 4, x cubed, no, x squared, and 16. For the x term, there was no constant, okay? And we get all the coordinates of x when the derivative is 0. Now, we already knew about the 2, so the other 2 coordinates were negative 2 and 0. Write down the intervals where the gradient is positive. Okay, so if we open a graph document and graph the function, which was, actually, okay, negative x to the 4 plus 8x squared plus 5, we get this. So we want to know when it's positive. So that's when the curve is increasing. So that would be in this area and this area. So that would be when x is less than the negative 2, because we know the minimum happens at negative 2. And it would be between x is 0 and positive 2, because we know what the x-coordinates of the other stationary points were. Okay, write down the range of f. Well, I would need to know the maximum, so if I menu analyze graph maximum between there and there, I get 21, so the range would be y is less than or equal to 21. And find the number of possible solutions when fx equals 5. So if we actually graph y equals 5, we can see it intersects with the curve 3 times, so it'll have 3 solutions. And for the equation fx is m, where m is just a real number, constant, it has 4 solutions. Find the possible values of m. So it's important that students understand that we need the horizontal line to cross the curve 4 times, and that'll be between when m is 5 and this top y value, which is 21. And that's all from me. I hope that was helpful.
That's fantastic. Thanks, Joanna. And
Thank you.
It's really nice to see a professional in action where you start losing your voice, and all of us as teachers were going, oh, we know what that's like, and you just kept on going. So well done, you.
Oh, thank you.
We're all feeling the same.
Thank you.
All right. Well, I'm just making sure that people can see my screen. So you guys have all been pros at that, and now here I am, not doing it quite as well. There we go. So thank you, Joanna, for
thank you.
A lot of information there, and Bojana earlier as well for everything you shared with us.
Thank you.
Some really nice feedback from all the people tonight, so thank you very much. And Joanna and Bojana will be just keeping an eye on the chat room just as we wrap things up. So if you do have any last-minute questions, please try and get those asked, so I know Bojana and Joanna will endeavour to answer them, or equally we'll add them to planning of future webinars. When you leave the webinar tonight, a brief survey will automatically appear here in your browser. Your feedback does guide us as we plan future online events, and we do listen to your feedback, so we do hope you share your thoughts in a post-webinar survey. And your certificates of attendance will be emailed to you in the next 48 hours, along with, as I mentioned, a link to the on-demand and YouTube version of the recording, as well as any relevant documents. After we leave tonight, if you do have any post-webinar follow-up and you want any, please feel free to phone or email. I know that TI Australia would love to hear from you, answer your questions where they can, and equally put you in touch with any TI trainers around Australia who can help and advise you. And that brings us, sadly, to the end of tonight's webinar. Thank you so much, Bojana and Joanna, for everything you shared with us. Really appreciate it.
Thank you
again.
Thank you, and thanks everyone else for joining us tonight. I hope you found it useful, and you can pass some of that on to your students to make them perform even better, both in their understanding of mathematics and in their test and exam. And hopefully we'll see you back online again soon. Thank you very much, and good evening.